Hello everyone, my name is Walter and I'm going to be presenting on experimental demonstration of brine concentration via air gap diffusion distillation. So with the growing increase of population, there's been a huge demand for water. And it has been projected that by 2040, a large portion of the global population is going to be experiencing high to extremely high water stress. So one way we combat this is through a process called desalination, which most of you are already familiar with. But the way this process works is that you take your saline stream, you go through some desalination process, it gives you fresh water and brine. But with the increase in these desalination technologies, there's an issue with the management of the brine. And so currently these brines are either dumped into the ocean or either sent underground. And this has a lot of environmental issues with it, but it also becomes very challenging when you're doing inland desalination. So one way people have tried to address this issue is through a process known as zero liquid discharge, which is the process of just extracting 90 to 98% of the water from that brine stream, leaving you a solid waste, which is a lot easier to dispose of or potentially repurpose. And so the way that zero liquid discharge works is that you take a conventional desalination technology such as RO, and you take that incoming feed stream, in this case, let's say seawater, and you'll get some permeate from it, or fresh water, it's also known as, and you recover up to 40 to 50% of the water. At that point, you're left with this brine stream, which is what I mentioned earlier. This brine stream is then sent to a brine concentrator, typically mechanical vapor compression. And at this point, it recovers around 80 to 90% of the water. After that point, the brine from the brine concentrator is then reached a salinity of about 20 weight percent, and this state is also known as minimum liquid discharge. And at that point, the final stage is a brine crystallizer or an evaporative pond. And at this point, the remaining amount of water is removed, giving you your 98% recovery, leaving you with just solid waste. So you can see that some benefits of this process is that you can extract 90 to 98% of the water, it enables salt recovery, and it allows desalination to be moved inland, which is what a current issue that desalination technologies that's trying to get to these salinities are having. But some disadvantages with this technology is that getting to zero liquid discharge, you can imagine, is very energy intensive. And the surfaces, specifically in the brine concentrator, are typically metallic. And when salt is exposed to metals, over time they begin to corrode. And so they're corroding, and so you have to replace them, or it makes the system expensive using corrosion resistant material. And you have to worry about scaling from the salt on these surfaces, limiting the heat transfer that takes place. So one way we want to combat this is through a process that what my thesis has been on, and that's through air gap diffusion distillation. And so the way that air gap diffusion distillation works is that you have two major components. One is the condenser channel, and another is an air evaporator. And these two components are separated by an air gap. And the way that we would be desalinating this brine stream is that you would take your incoming feed stream, flow it through the condenser channel, and then you will apply some external heat, heating it up to the desired set point. After it's heated up to the desired set point, it will flow along the evaporator surface, and then due to the temperature difference between the evaporator surface and the condenser side, you have water vapor that's leaving the evaporator to condense on the external surface of the condenser, giving you your permeate. Afterwards, you have this remaining stream of brine that gets circulated out. And with this process, you might have noticed that it mimics a counterflow heat exchanger design. So with the incoming feed stream, there's going to be some preheating that takes place, allowing you to recover some of the heat that takes place. And another benefit of this system is that it operates at ambient conditions, so there's no vacuuming conditions necessary for it to work. And the one major benefit that this system offers is that it's completely made out of polymers, meaning that polymers are inherently corrosive resistant, so they don't have to worry about that corrosive nature that salt provides. And Unlike some other AGDD variations that using a wicking structure, ours doesn't have to worry about that. So we don't have to worry about these clogging of like pores within these other wicking or fabric structures that have been used in other variations of AGDD. And so I developed a couple heat and mass transfer model for this system, but for this presentation, I'm going to be primarily going over the experimental demonstration, but you guys can access the paper that we did to describe modeling with this QR code. So I would like to just mention some of the key nuances with AGDD. We have heat and mass transfer taking place across the air gap channel. So this is a thermal resistant network of the for AGDD system. And then here's the mass resistance for the system. And the only mass transfer that we have taking place is through the air gap. And you guys might have realized that this is a kind of a variation of membrane distillation. But the main thing that we are doing that's different from MD is that we remove the membrane. And so in this case with AGMD, you have an added thermal resistance, which is indicated by that green block. And you also have an added mass transfer resistance due to the membrane. And so when we want to look at how do we space the evaporator and condenser between each other, we see that there's an optimal air gap before both cases. And because we don't have that added mass transfer resistance, because we lack that membrane, we can get to larger air gap spacing and still compare to AGMD. And so when we model this system, these are some of the input conditions that we had to it, and then you can see that this is what our temperature profile looks like. And as I mentioned earlier, this mimics a counterflow heat exchanger, which is indicated by this plot. And some performance metrics when you're typically dealing with thermal desalination system is the GOR. And so the GOR is a way of indicating how well you are recovering the thermal energy within your system. And in this case, we had a GOR of 6 based off the modeling, and this showed that we were able to recover the heat roughly 6 times. And then for the water recovery, we show that in one pass, we can get roughly about 9% water recovery in one pass. And I'll later discuss why, how do we get to the higher salinity desalination later in the presentation. So for the prototype of this system, so currently I've just talked about like theory of what the system does. This is a blown up exploded view of a SolidWorks file that I made that shows how this system looks like. And so for this setup, we have the evaporator surface. We have our air gap spacer, which is just a piece of material machine that basically fixed the specified air gap. Next, we have our condenser plate and condenser backplate, and these two are put together to make the condenser channel. And then all of these components are separated with the gasket to help prevent leaks. And then so the way that the fluid flows through the system is that we have our condenser inlet here. The fluid then comes out and gets sent to a heat exchanger, and then it gets sent to our evaporator inlet, and then it comes out. And so for the overall dimensions of this prototype, it was roughly 10 inches wide and about 25 inches tall. And so one thing you might have seen on the evaporator side is that instead of the brine stream flowing vertically down, we had it going in a serpentine-like channel, and that was primarily to enhance the amount of surface area exposed to the evaporator surface. And here's what, like a zoomed up view of what the evaporator channels are looking like. And then from the setup, we made this system completely out of acrylic. And our air gap spacer in this prototype setup was about 5 millimeters thick. And because we have these serpentine channels, we're not getting that full area coverage, but we got roughly 80% area coverage with the channels taking up some of that area. So to go on to that experimental setup, this is the layout of how the parametrics, when we did our parametric analysis, how it was conducted. So you take your feed stream and then you flow it through a cold side heat exchanger, which rejects some of that heat. Then that brine stream that exits the cold side heat exchanger goes to the condenser channel. Then it gets pumped into a hot side heat exchanger, heats up to the desired set point, and comes out, and we collect that brine stream in a separate jar. And this was, the reason we kept them in 2 separate jars is that way we can make sure the inlet salinity into our system when we're testing is fixed. And so some of the flow rates that we tested were about 1.5 and 3 kilograms per hour, and we had an evaporator inlet temperature of around 90 C. And so for this parametric study, this was strictly for a single pass. And what we did we recorded the permeate using a mass, so a mass seated at the bottom of the system, and we let it drip down into a beaker where we recorded over time. And all the testing was done over a 5-hour interval. And these heat exchangers were custom made, so we just made them in lab just for these specific purposes. And so when we look at the temperature profile, we see that we get fairly good agreement between the evaporator and condenser side for a 90 degrees C inlet temperature for the 1.5 and 3 kilograms per hour flow rate. We saw that we had about a increase of 20 degrees to 30 degrees C temperature difference between the evaporator and condenser side. And we had roughly about a 16% difference of experimental results compared to the theoretical model. And so when we look at the amount of permeate collected, we see that there is some slight deviation for the permeate collection from the feed stream for the different flow rates that we chose. And that was roughly 22 to 29% for those two respective flow rates, and I will explain later why we saw those deviations. And then when we looked at the GOR, we had some good agreement on for the 3 kilograms per hour, but there was still deviation for the 1.5 kilograms per hour flow rate. And we saw that there was roughly 24 to 16% difference respectively for those two flow rate ranges. And then, but we did see that when we tested the amount of quality that the permeate we collected was roughly 0.05 weight percent, which was still drinkable water, which was good to see in our experiments. And so there were the reason for the discrepancy for the amount of permeate collected was inherently due to the evaporator design. So as I mentioned before, we had to have these evaporator channels to help maximize the area of the flow rate. And so we built, to confirm that theory, we built a smaller scale setup where we had a hot plate heat up a beaker of saline solution, and we pumped the saline solution through a small scale evaporator surface. And the water just evaporated to the ambient. We didn't care about collecting it. We just wanted to see what was happening on the evaporator surface. And for this evaporator surface, it was roughly like 6 inches wide and 3 inches tall. And then, like I said, the water just evaporated into the environment. And we saw that when we were flowing the brine stream through the system at 0 minutes, we don't see nothing because we just started. Then after 60 minutes, we start to see that water vapor starts to condense on the top walls and side walls of our surface, which was indicating, okay, maybe we're losing some of that water we should be collecting on the condenser side to the evaporator side. And so we recorded it even longer. So after a longer period of time, we saw that these permeate droplets start to increase. And then after even further time, we saw that these droplets grew. So this was confirming that some of the water that's leaving the evaporator's surface is either condensing on these external walls and then reforming back into the brine solution. And so that let us know that though the system works, we do need to work on improving the evaporator side to help maximize the amount of permeate that we are collecting. But now that we've shown that the system works, even though we have there's some things that we still need to address, we wanted to test this system at MLD. And so the main difference between the parametric study versus the MLD experiment study is that instead of having 2 reservoirs where the brine stream flows into a separate jar, we kept recirculating in the same jar and thus concentrating that feed stream all the way up until we got to the desired salinity. And in this case, we had a 9-liter jar, and we concentrated and we removed enough water until we were left with about 2.5 liters left of solution, which when you do the math, equates around to 20 weight percent salinity for this feed stream. And it took roughly 23 passes for this system to flow through the whole setup. And then what we saw was that we were able to recover approximately 70% of the water from the brine stream, which equated to around 6.5 liters of permeate. And then from the results, we were able to show that we were able to achieve MLD with this AGDD setup. And here were the final salinities. So we measured the salinities of the feed and initial feed stream and then the permeate using an activity meter. And we saw that when we convert those back to salinities, we had our initial feed stream was about 7.21 weight percent, and then our final salinity stream was roughly 20 weight percent, and then our permeate was about 0.04 weight percent. So now that we've shown that we can get up to MLD with this like setup, and we didn't have any issues with salt precipitating or forming on the surface, we wanted to see what happens if we take this up to ZLD. So basically, we just start extracting the remaining amount of water. And so the way this is set up is that we started off with a 20 weight percent solution. Since there was no point in trying to start all the way from 3 and work our way up to 20, let's just start off with the final salinity that the AGDD setup ended at. And we heated up a hot plate up to 80 degrees C, and which heated up our reservoir solution. And basically similar to how I checked the discrepancies in the permeate collected, I basically performed that same process, but instead I'm evaporating all the water to see how much salt has precipitated on the surface. And so the way that this looks like is that same setup that I shown earlier. I evaporated all the water. Next, we start to see that salt starts to form on the surface over time because they're starting to precipitate. Next, once we evaporated all the water, we weighed the sample to see how much salt has accumulated on the surface. And then next, we did a cleaning step where we flow DI water, but just to note, it doesn't have to be DI water, it just has to be a solution that has a lower salinity than the, just a lower salinity to help redissolve the salts. And then after that, we basically clean the surface and then measure the evaporated surface final weight, and to see if we were able to bring it back to its initial state. And so what we saw is that here's the initial state of the surface, and then after we got up to ZLD, this is what the surface looks like when you have salt precipitated. And then after you start to flow the cleansing solution through the evaporated surface, we're able to redissolve all the water, bringing it back to our initial state. And then thus showing that this system could be easily cleaned or be used to help get to ZLD, because we don't have to worry about the salt adhering or scaling the surface. We can just easily clean it off. So in this presentation, I performed a parametric study that helped to validate the theoretical results. I was able to demonstrate ZLD, which basically taking the brine solution from a 7 weight percent solution down to 20 weight percent. Next, I was able to demonstrate not only MLD, but also ZLD conditions. And then lastly, I was able to show that because this AGD system is made out of polymers, it was able to prevent salt precipitation and the corrosive nature of the saline solution on the system. And then I was able to show that the precipitated salt under ZLD conditions can efficiently be cleaned in the AGD setup. And in some future works that I have to come do is do a more thorough durability study, because right now I just only tested it with NaCl, but the next thing will be tested with a more complex brine solution that has other components within it to see how robust it is at removing these other components. Next, I want to flush out the evaporator design to see how I can improve it to minimize the loss of water vapor from that to the evaporator surface. And then a next test of the brine streams in a full setup for MLD and ZLD conditions. And lastly, here's a picture of like what the experimental setup looks like. And then lastly, I would like to just thank my lab mates. Shout out to Dr. Mike Adams, Dr. Jordan Coulter, and then TK Kim.